Yes, it's a great pleasure to be here and tell you about our recent results from the Muon g-2 experiment. So here's a picture. This is about 2014, I think, 2013, of the parts of the experiment arriving at Fermilab. And this is a real picture. It's not like false color. It's those of you being in the Chicago area, and I'm not a native out there, but it's just amazing the kind of weather and skies you get out there. So, and the tornado warnings also are interesting. So the goal of this experiment is to make a measurement of the Muon magnetic moment anomaly to a precision of 140 parts per billion. So I'll tell you what the importance of this is and why this particular precision would be of interest. So first, take a step back a couple of years. April 7th, 2021. Our experiment got plastered all over the papers, and I was surprised at the interest in this. And in particular, some of the headlines were, you could tell they're written by people who didn't quite understand what was going on. But for instance, the New York Times, a particle's tiny wobble could upend the known laws of physics. So today I'll tell you the story. Okay, what is all this fuss about? Can the known laws of physics really be overturned? And of course, we know they can't. What is the Muon g-2 experiment all about? How does it work? What did we find, and what's going to happen next? So this is a talk primarily about the standard model of physics, so about the particles and the forces of the standard model. So with the discovery of the Higgs boson in 2012, all of the particles predicted in the standard model have been discovered, and we know how the particles interact through these force carriers here. And in particular, all you have to do is solve the equations of the standard model Lagrangian on the right-hand side. And so that's our homework for the next 100 years. So there are many interesting features of this, but one of the interesting things is that everyday matter is just made of the particles in the first family here. But what I'll tell you about is about the muon, which was the first particle which was discovered from the second generation of particles in 1936. So what is a muon? Well, a muon is very much like an electron. It has the same charge, and its interactions are identical to the electron. And it was discovered in cosmic rays in 1936. The way that the muon is different from an electron is that it's much heavier. It's about 207 times heavier, and it's unstable. It decays at rest in about 2.2 microseconds. So not a lot of time to do experiments on it. And again, it belongs to the second family, who we don't know why there's a second family. And it's not found in ordinary matter, but it is produced constantly in cosmic rays. So if you take a look up here, you have a primary cosmic ray hitting the upper atmosphere. It produces a lot of particles, including pions, and then the pions can decay into muons and neutrinos. So we can exploit this process. If we can make pions in the lab, let them decay, we can grab these muons and then do an experiment. Okay. So I told you this is about the standard model. So the standard model is incredibly successful. And let me, as an example, let me tell you about a measurement of the electron magnetic moment. Okay. So this is from February of this year. And what they did, these experimenters, Jerry Gabriels and collaborators, is they made a penning trap for a single electron. So they made a strong magnetic field that would confine the electron in the radial direction. And then they had electrodes on the upper and lower surfaces for vertical confinement, and they would trap a single electron for months and observe its properties. And the thing they were interested in is its magnetic moment. So the magnetic moment is proportional to the charge to mass ratio, the spin angular momentum of the particle, and then this dimensionless factor out in front called the G factor. And they were making a precision measurement of this G factor of the electron. The interesting thing about the G factor is that it's something that can be predicted in the standard model. And I said to high precision, but really, I probably should have said ultra high or something like that. So in quantum field theory, the whizzes learned how to calculate the G factor of the electron in an expansion in the fine structure constant. And then there are also these other somewhat difficult to, well, all of these terms are difficult to calculate, but even more difficult terms to calculate. So they measured, there are predictions for the G factor of the electron, and there are measurements, and let me show you how those pair up. Here's the G factor measurement of 2022, and then, or sorry, here's 2008, 2022, the new result. And these are comparisons with theoretical models. Obviously, the theory depends on your value for alpha. So if you want to make a high precision measurement of, or comparison with the G factor, you need a high precision measurement of alpha. At the moment, there are two measurements of alpha of comparable precision, but they have a slight discrepancy, one based on recoil and rubidium atoms, and then Holger-Mueller's experiment with cesium. So there's a slight difference between these two, so you get a different prediction. And there's also some uncertainty in this term here. But what we should be doing is comparing the experimental value with these theoretical values. But the thing to pay attention to is look at the number of digits down here. So the agreement is down at this digit down here. Okay. So the theory and the experiment agree to 12 significant figures. And to my knowledge, this is the most accurately verified prediction in any field of human knowledge. Okay. The most accurate prediction, and it's not the most accurate measurement, but it's the thing about which we can make the most accurate prediction. Yeah. Yeah. I'll show you. Yeah. Yeah. In the context of the muon. Actually, I made a mistake. That should have been. Oh, sorry. Yeah, that's. Yeah, these are mu and tau. Yeah, I'll show you the kind of the relevant Feynman diagrams. Anyway, so the message here is that the standard model works incredibly well in some contexts. On the other hand, we all know that there are glaring, enormous deficiencies in the standard model, and many of these deficiencies are being addressed by people in this room. So, of course, we don't fully understand gravity. And in fact, we don't really understand most of the universe. We understand perhaps 5% of it. We don't know really the origin of dark matter or its nature. We don't know about dark energy, which constitutes maybe 70% of the energy density of the universe. We don't know why, the particle table I showed you, why these particle masses should vary so much over, almost 10 orders of magnitude. Why are there 3 families of particles? Why is there more matter than antimatter? So there are so many things we don't understand. And yet on the other side, the things that we do understand, say this 5% of the universe, we know extraordinarily well. So how are we going to make progress? How are we going to address some of these mysteries? Well, of course, the people who are much smarter than I am propose improvements to the standard model. You look at how it's deficient and how it could be extended to solve some of these problems. And typically, these solutions always involve new particles or new forces, right? And they will yield testable predictions. And so as an experimentalist, what we can do is go and test these predictions. And any number of ways of doing this. You can make ever higher energy collisions at the LHC or with ever higher luminosity. You can look for new phenomena at low energies. You can look for new things that are whose signature in the standard model is suppressed, like electric dipole moments. You can look for new phenomena like axions, dark matter. There's a whole bunch of ways we can address the deficiencies of the standard model. One in particular that everybody had great hopes in was supersymmetry. And we had this impression if you turn on the LHC and your detector would be, overwhelmed with supersymmetric particles flying everywhere. And it just didn't happen. There's this kind of depressing article, why supersymmetry may be the greatest failed prediction in particle physics. We're not. Oh, okay. Okay. Yeah. Okay. Yeah. I mean, the story's not over, right? LHC is running. They're run highly. Like it may be just around the corner. We never know. It's what makes it exciting, right? Yeah. Right. Well, fusion. Now. It really is around the corner, right? Maybe, but it's yeah. Yeah. Now they've got it. Yeah. So it's yeah. So we can hope for the same thing. I'm certainly optimistic. Yeah. But this is kind of where we are now, right? Like, it's been LHC it's been on for quite a while. We just haven't found any new particles. We haven't found any new forces, and everything we do in the lab basically just gives us a standard model answer. But we know that new physics is out there. We just have to be persistent and go after it. Okay, So let me take a step back a little bit to a few years ago, so around 2017. And I told you a little bit about the electrons' magnetic moment. Let me tell you a little bit about the muons' magnetic moment. So on this plot, I show the measured value of the magnetic moment anomaly. I'll get to what that is in a second. Of the muon from the result of a Brookhaven experiment. And the final final result from this experiment came out in about 2006. And all the while, theorists were working on their predictions for what this value could be. And it was fairly stable. And around 2017, there was a sort of definitive work. And this was the standard model prediction. Here was the experiment. And clearly, they're discrepant, right, to some level. And it's unclear what this is, right? But it could be, in particle physics, we make. This is 10 to the minus 11. Yeah, sorry. Yeah. In particle physics, you make, hundreds, if not thousands of measurements. So some fraction are just going to be in those tails, the statistical tails, right? So maybe this is just one of them, right? But it's worth exploring. Yeah, I could pull the slide. There we go. Yeah, okay, yeah. Yeah. So maybe this was just in a tail of some distribution. Maybe it's something new. People figured we knew how to do it better. So maybe we could try and see if we could do a better job on it. So first, let me take a step back. I've thrown some terms like the magnetic moment, the magnetic moment anomaly. So let's just go and review what those things mean. So a magnetic dipole moment you can make just from a current loop, right? And the magnetic moment would be given by the current in the loop, the area of the loop, and if you like CGS units that I refuse to give up, then you divide by C. Okay, so the current in the loop, it's the charge divided by the time it takes to go around, so that would be the circumference divided by the velocity. The area of the loop is pi r squared. We multiply by the mass on top and bottom, and you see that you can express the magnetic moment in terms of the charge to mass ratio and the orbital angular momentum. So this worked for quite a while, but in the 20s, people were doing surprisingly accurate spectroscopy, and they noticed something, the anomalous Zeeman effect, where if you put an atom in a magnetic field, they noticed that in some cases you'd get an odd number of lines, in some cases you would get an even number of lines, and this could not be explained. And Pauli suggested, not only the number of lines was odd, but also the magnitude of the splittings you would get was also odd. So Pauli proposed that another quantum number was needed, and Ralph Koenig and I can't remember his colleague also proposed, maybe the electron has spin, and Pauli rejected this as unrealistic. And Uhlenbeck and Goudsmit picked up the idea and proposed electron spin and actually submitted a paper on this, but they were very nervous about the whole idea and wanted to retract it. So what this would do is it would contribute, if the electron had its own angular momentum, then that would make it, then it would have an associated magnetic moment. And we wouldn't know in advance the strength of this magnetic moment, so you could put a little dimensionless number out in front to characterize its strength. And to match the spectroscopy, this number had to be 2. And that was a little strange, right? Because there's a 1 in front of the orbital angular momentum. Why would you need a 2 in front of the spin? So these splittings could be explained by half-integer spin and the dimensionless factor g equals 2. And then things really came together in the 28 when Dirac proposed, he had his relativistic theory of quantum mechanics, and he showed that g should be 2 for a fundamental spin half particle. This was a huge success. Like finally, everything sort of made sense. Shortly after, Otto Stern proposed, let's measure g of the proton. Let's just check this out. Pauli says, don't you know the Dirac theory? It's obvious g of the proton is going to be 2. And we know what happened. Stern found that g of the proton is 5.6, right? And this, you could say, is the first magnetic moment anomaly. And in retrospect, now we know this was an indication of proton substructure. But at the time, it was, where on earth did this come from? But, you could, of course, develop this if you have some composite object. Yeah.
Is Pauli ever known to
I don't. Yeah, I'm really painting him out to be the bad guy here. But, of course, yeah. He was, I think he was pretty critical. But on the other hand, he was.
to, get the idea. But even then, you can get this I think that the topic.
Yeah. Right.
Then you get it out.
It did.
But in a very weird sense, we also do that with the
And good, yeah.
because they didn't give them the Nobel Prize,
Yeah.
because they couldn't give it to Corona. Right? So it's something.
Yeah. It had implications.
No, we've got a real strong.
Yeah. So the story doesn't end there. So now I'm going to turn to the anomaly. So we just talked about the magnetic moment. Let's talk about the anomaly. So progress, there was lots of progress in spectroscopy, and around in the late 40s, Rabi and his collaborators, Rafe and Nelson, they were looking at ground state hyperfine structure in hydrogen and deuterium, and Cush and Foley, they were all at Columbia. They were looking at, they found these discrepancies in the spectroscopy of gallium. And the way things could be explained, actually, Gregory Bright, I think, had something to do with this, was that the G factor, you could explain things if the G factor of the electron, instead of being identically equal to 2, had this additional amount here. So everything could be explained if it were not identically equal to 2, but had this anomalous correction here. And at the same time, Schwinger was working on what Schwinger did, or all of this theory of QED, and he showed, in fact, that the G factor of the electron should be modified by alpha over 2 pi, and these guys were in perfect agreement. So, in fact, nowadays, we talk about the G factor being 2 times 1 plus some anomalous part. So this is the magnetic moment anomaly, and it's given by G minus 2 over 2. And back in the first contribution is of order alpha over 2 pi. So in the sort of modern picture of Feynman diagrams, the way you might look at this is, here's an electron interacting with the virtual photon of a magnetic field, and what Schwinger showed is that you have this kind of bare diagram here, but in addition, the electron could exchange an additional virtual photon with itself, and this modifies the interaction of the electron with the magnetic field and modifies the G factor of the electron. So this anomaly is due to radiative corrections from virtual particles of loops. So it's a tiny effect, right? This is 1 part in 850, but it was a huge success for QED. Like, this was the birth of QED. Now, fortunately or unfortunately, radiative corrections don't end with the exchange of a single virtual photon. In fact, it gets very hairy. So these are, to go back to the question, these are some of the QED diagrams that would be that if you want to make a prediction for the magnetic moment anomaly, you would have to calculate these Feynman diagrams. Okay, so you could have a virtual photon. The virtual photon turns into an electron-positron pair that could recombine and give you back a virtual photon. You could have this plus the exchange of another virtual photon, and so on. You could also have Z bosons exchange W bosons. Even the Higgs boson makes a tiny contribution to the G factor, or to the magnetic moment anomaly. You can even have entire hadrons appearing in these loops. Pions, protons, whatever will be in these loops. And you can imagine how difficult that would be to calculate. Then, of course, it could occur at higher order, where you have these additional exchanges. Finally, there's this term. So these are called the hadronic vacuum polarization terms. And then you have this hadronic light by light term, which looks like light scattering off of light with this hadronic blob in the middle. So the many interesting things about this is that the magnetic moment anomaly, because it's sensitive to radiative corrections, it actually gets contributions from all the physics. All the standard model particles appear in these loops. And perhaps the most interesting, yeah. They're but they appear as bound states, yeah, and yeah.
So they technically just a
yeah. I've asked them here, why don't we just draw this with quark loops? And I actually have not gotten a straight answer on that. So it's like it's not perturbative. Like we can draw all the other
Okay.
It's non-perturbative here. Yeah.
So let's just start in the diagram.
Yeah. Yeah. So the interesting thing is, again, these are photons.
Down there.
Oh, these are photons. Yeah. And so inside here, there are gluons. Yeah. Yeah.
So basically, when you get carbonate, what they carbonate.
Yes. Yeah. 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 And that's not, yeah. So we will talk about, yeah, other ways of addressing that issue. Oh, sorry. Now, the other thing, of course, is that we don't know everything in particle physics. So, of course, if there are new particles, they will make their appearance in these loops. Okay, so the measured value of the magnetic moment anomaly gets contributions from all the standard model particles plus the unknown particles we don't know about. Okay, so that's the idea. So here's what we're going to do. So, maybe the magnetic moment anomaly, for sure, it's affected by any new particles that are not included in the standard model. And those, of course, would not be included in a prediction because you can't include things you don't know about. So the theorists will make a prediction. We're going to make a measurement, and then we're going to compare them. So, of course, if we find a discrepancy, that's going to be very interesting. That would, of course, imply new physics. But even agreement is helpful, too, because whatever theory of nature you're going to make, it's going to have to be consistent with the measurement. So if we can make a measurement with tiny, like excruciatingly tiny error bars, it's going to be very hard to make some generic theory of nature match that unless it has particular properties. So the smaller our uncertainties, the better the test we make of the standard model, and also the more it tells us about physics beyond the standard model. And of course, even if we find a discrepancy, it's not that the standard model is wrong, it's just incomplete. We know it's incomplete. We know that there must be new particles out there. Sorry? Right, yeah. Yeah. Yeah.
Yeah. So this slide is going to be unknown particles.
Yeah.
So when the particular final diagram, you have to use that different particles.
Right. Right. So people, you would put in, so you make your supersymmetric model of nature, and you would know the nature. I mean, you would parameterize your coupling. So you'd put it in, and the influence of these particles would include an uncertain, like their influence on a mu would be, it's not well defined. It's only, it would depend on the coupling size. So you can put limits on the size of these couplings or the masses of these particles. Yeah. Right. That would just depend on your theory. Right. Yeah. It's generically, so it would depend on the sensitivity of the experiment, right? But in principle, this will occur for any, like the Higgs boson contribution is at the 10 to the minus 12 level, like it's beyond what we can see. So depending on the masses of these particles and the couplings, we would not be sensitive to it depending on the experimental sensitivity. Yeah. But it would be highly model dependent, the contribution of any particular.
They could still be new physics.
Right, but we're not sensitive enough to it. Yeah. So that's the thing. We know the new physics is in there, but we might need an experiment we just cannot do to see it. Yeah. So the first part of our endeavor here is for the theorists to try to make a definitive standard model prediction for the electron muon magnetic moment anomaly. So a collaboration was formed called the Muon g-2 Theory Initiative. It's hosted by Ida El-Khadra at University of Illinois. It's a collaboration of more than 100 theorists. They've held 9 meetings since 2017, and their goal is to study all of the standard model inputs and make a definitive prediction of the magnetic moment anomaly. They've come out with a first published report in 2020. This is 166 pages long. It has 132 authors, 822 references. Like it's an encyclopedic kind of look at a single number. It's really incredible. And so we're going to compare our results with what they predicted. And of course, this is theoretical work. It's ongoing, and there's actually plenty to do, as we'll discover by the end of our discussion today. And they do hope to provide an update in 2025 or so. Okay, so to go back to some of these Feynman diagram calculations, or like how would you predict g-2 of the electron? So here's the QED contribution. This is 99.999994% of everything but 60 parts per million is from the QED contribution. It's being calculated up to the 10th order. So basically there are 10 vertices here. There are 12,672 Feynman diagrams involved here. So that, it's like the world's worst homework problem. It takes decades to do this work, but this is again, like look at this precision. Like how many things in physics can we say we're confident in with this level of precision? It's absolutely astonishing. Yeah, there's a lot of Yeah, so you don't have to calculate every single one. There are lots of symmetries and things and cancellations that they figured out in order. Yes, yeah. So here's the electroweak contribution. There are 6 to 2 loops. There's 1,678 diagrams. So this was the first full computation in the standard model at 2 loops. This term is very well determined. It's a small part. It's only 1.3 parts per million contribution, but it's extremely well known. Now the hadronic part is very interesting and very challenging. Okay, so one approach to this is that you could look at this Feynman diagram, and then from analyticity and unitarity, you can see that there's a relationship between this amplitude here and that for electron-positron annihilation into hadrons. Okay. So you can relate these two. And then your job is to make precision measurements of absolute cross-sections in E plus E minus annihilation. And so if you measure E minus going to hadrons, there's a kernel function that tells you how to weight the center of mass energy. And you can integrate this up and determine this hadronic vacuum polarization contribution. A couple of things to note is that this integral is weighted to low center of mass energies, low S. So we don't have to do these experiments to super high energy. Only the low energies really matter. And there are a couple of ways of doing this. There are some machines where you can change the energy of the colliding beams. And so that's one way of scanning the center of mass energy. So you could just make the measurements of the cross sections, you change your center of mass energy. Another approach is that you could look for initial state radiation that effectively changes the center of mass energy at the collision, and then you can measure your cross sections that way. So there have been dozens of experiments doing this over decades, measuring these cross sections, and the data from these experiments has to be combined. So this is what it looks like. This is the ratio of electron-positron pairs going to hadrons over that for E plus E minus going to muons. And so this is what these cross-section data look like. Most of the contribution to the vacuum polarization to the muon comes down below for root S below 2 GeV. So down here is the most important region. The stuff up here on the right-hand side is less of, but even down here, it's incredibly complicated. The most important region is just for E plus E minus goes to pi plus pi minus. But once you get up here, there are many, many, many final states. And so in the end, just to get this plot, you have to combine something like 50 exclusive channels. You have to deal with radiative corrections. You have to deal with dozens of different experiments who've handled things in different ways. It's an extremely challenging operation. Yeah. You can up here, but here people wanted to do the exclusive measurements. Yeah. Why not?
All you care about
is the total hadrons. Yeah.
Hadron. Why do you care which hadron is going into?
Yeah. Well, down here you can. I mean, I guess it's historical, right? Like the data. People didn't know. I just want to do E plus E minus going to hadrons.
Right. You mentioned that close to the transition point, there are many final states.
Right. It just experimentally, people want to measure. You want to have your identified particles, and then you can just combine it. Right. It's just the way the experimental work is done.
The same contribution into that.
People. It's being studied. I can't answer that as a practitioner here. I can just say that it's being looked at very carefully in constructing there's not really a hard transition point. It's just the way they've had to combine the data. But those of you who are doing experimental particle physics measurements, and I've worked on some. If you ask someone to do, an absolute cross-section measurement to 0.5% uncertainty, that's incredibly challenging. But this is what's been achieved by these various collaborations over many years. So here, if you take this data, put it into that function I showed earlier, you get this contribution of the hadronic vacuum polarization. And again, it's about 60 parts per million. But this is the term with the most uncertainty, and it's almost for obvious reasons. Like, this is incredibly difficult. These are just resonant effects. Yeah.
Right.
Yeah.
Yeah, that's not fine. Resonance, that is going up, and then it starts going down.
On which,
So you just say you move now the resonance. Then you go up, and then it goes around. And
that's just the resonance phenomenon. Yeah.
The width of the bow is like 170. Oh, I see.
Yeah. It's very, yeah. These are pretty narrow. Yeah. And the size, these guys are even narrower. Okay, the final term is this hadronic light by light contribution. This is even more difficult than the hadronic vacuum polarization. And historically, actually till recently, there were just people had sort of, I wouldn't say they're vague conceptions, but just highly model dependent ways of looking at this. But more recently, it's been put on fairly firm theoretical foundations. There's a way now, a data-driven dispersive approach to this. So there's now a kind of prescription to determine this term in two ways. One of them is data-driven, as I just mentioned, and the other one is using lattice QCD. And then the data-driven one, here's one way you could look at this diagram. Well, you could these two virtual photons, that are essentially a pi naught, and then the pi naught decays to two virtual photons, or an eta or eta prime or whatever. And so you can take data about the width of the pion and all of these form factors and these sorts of things, and use them as input into a calculation. So it's incredibly difficult, but at least there's a prescription, and people have been pursuing that. Because it looks like light scattering off of light, in a sense. Yeah. It's trivial. Yeah. So there are two approaches here. And what's interesting, so up till about 2020, there were these highly model dependent ones. The white paper came out, and since then there's been this, before the white paper, there was a lot of progress in these dispersive methods plus data. So this approach with a very firm theoretical foundation that gave the white paper result. And since then, results on the lattice, and now you can see and dispersive results are pretty much in agreement. And here's the size of the term. It's the smallest contribution to A mu. It's known to about 20%, and people expect this uncertainty to go down to about the 10% level in a few years. Okay, so here's the result of 2020 for the prediction. These are, here's the QED term and its uncertainty, the electroweak term, its uncertainty, and the hadronic vacuum polarization term, its uncertainty, which dominates, and then the light by light, its magnitude and its uncertainty. This prediction has 8 significant figures. Again, this is a real triumph of the theorists in quantum field theory. So a prediction to 370 parts per billion. As far as I know, you could barely make predictions of that level, or maybe not even for something like the hydrogen atom, right? Because the proton is too complicated. You can't just, from first principles, make a prediction for the hydrogen atom. Okay, but you'll remember at the very beginning, I told you about the electron, where things have been measured to 12 significant figures. Why on earth would we bother with the muon? So the electron anomaly is known to 0.1 parts per billion. Muons live 2.2 microseconds. You have to get them from these complicated processes. Why would you bother? So there's one very important reason, and that goes back to these diagrams, where if you look at the contribution of the W-boson to the magnetic moment anomaly of the muon, the contribution goes like the mass of the muon over the mass of the W squared. Okay. Now, the same contribution for the electron would involve the mass of the electron over the mass of the W squared. So it's much, much smaller for the electron. So if you have these new particles that you're looking for, their contribution kind of generically for the electron would go like electron mass over mass of new particle squared. For the muon, it goes like muon mass over the new particle squared. So because the muon is about 207 times heavier, its new physics contribution is about 43,000 times larger. So as a way of probing for new physics, it's much better. You get this enhancement of 43,000. So to put it in perspective, a new physics contribution to 0.1 ppb on the electron anomaly, so this is the precision of the electron anomaly, that would correspond to a 4 ppm effect on the muon anomaly. Okay, so and we can do much better than 4 ppm on the measurement. So it becomes much more sensitive to new physics. So with lower precision, the muon anomaly is much more sensitive to higher mass scales, and it becomes a better test of the standard model. Yes. Yeah, so people looked at that. So the tau is 1.7 GeV or so. So you don't get that much more, and then it lives 10 to the 19 seconds or something. Like it's even harder to produce. So the argument kind of ends with the muon. Yeah. Okay, so how are we going to measure a magnetic moment? And there are no undergrads in here, so I will, I'll skip this. But everyone knows if you put a magnetic moment in a magnetic field, there's a torque, and the angular momentum will precess at some frequency omega, and this angular frequency omega is proportional to the external magnetic field and this gyromagnetic ratio of the particle. Okay, the gyromagnetic ratio is the thing that relates the magnetic moment to the orbital angular momentum. So to measure a magnetic moment, all you want to do is measure some precession frequency and measure your magnetic field, and then you can get the gyromagnetic ratio, or basically your G factor. Okay, so we formed an experiment to address this longstanding mystery with the Brookhaven result. Is this real physics, new physics, or is this just a statistical anomaly? And our goal again is to go to 140 parts per billion. So remember, this will be, more than like 40 times more sensitive to new physics than the electron anomaly. Okay, so rather than so I told you there was this Brookhaven experiment. Why don't we just go back to Brookhaven and try and do it better? Well, I'll tell you the reasons we went to Fermilab. But rather than just make a whole new experiment at Fermilab, we decided to move the storage ring to Brookhaven to save about $30 million. Otherwise, this, of course, would not happen. So this is what the experiment looked like at Brookhaven before the magnet was insulated. And you can just imagine confronting this and saying, okay, we're going to move this halfway across the country. If you start to look in the details, it's just crazy because, this is the so-called interconnect region here where the superconducting connections are made between coils up and down. Inside here are, I'm not kidding, thousands of wires. And if you look on the floor, like all of this stuff here has to be accounted for. But the engineers at Brookhaven did, an amazing job. Like the things were labeled, there were tables of, it was really done very, very professionally. So you could take this thing and you would know what these pins are for and all of these little connections. It was very, very professionally done. And it kind of became manageable. Like you could take it apart, label the parts, and then figure out how to put it back together again. But it really, when you confront this for the first time, you just think, this is crazy. This is when I worked at Brookhaven, I spent a lot of time with this machine, which was what we used to measure the magnetic field. And this is something we scrapped. There was no reason, it didn't even turn on when we tried it again. So, so that thankfully got left behind. But it really looked like an impossible job. But it got done. It took a few years, but we took the thing apart. The superconducting coils could not be taken apart, so they had to be transported together. There's a company called Amherst, which takes on impossible jobs. They will move, you call them in, can you please move this blah, blah, blah thing from here to here? They just say yes. And they figure out how to do it. It's like, I just love things like that in this country, right?
I wonder
Yeah.
if they're the same company, because there's a six-story building on the corner where I live,
Oh,
and they moved it one block.
okay. Yeah. It's like, yeah, I wonder, yeah. You could check and see. There, yeah, and it was even, this thing even appeared on some YouTube video for amazing moves or something like it just ran, like it was very strange. Like I think this company also moved the space shuttle into LA when they parked one there, and some giant boulder, which is apparently a piece of art. No, fortunately, we that would be step too far, bridge too far. Yeah. So they just had to be, highly stabilized. The things couldn't be more than about a millimeter. So the parts went down the east coast of the U.S. and then up the Mississippi. Had quite a and people came out to, like, local news crews videotape this thing going by, and because it just looked like a strange, very strange thing. And finally made its way to Fermilab in 2013. And there were lots of people interested just to see this crazy thing arrive. Yeah. Yeah.
It's too bad you guys could have taken it past Area 51.
Yeah. Well, that's the thing. Someone, So, well, I don't know if any of you have worked out at Brookhaven, but there were always, people always wondered if, there were aliens harbored on site, and they see this. There was some message someone scrawled in marker on this thing having to do with UFOs or, Area 51 or something like this. But there are definitely people who are very curious about this stuff. But one thing was that those of you, being to the Chicago area, just the enormous number of tolls and arches and things. So this thing just fit with 6 inches clearance on either side, and had that not been possible, I'm sure the experiment would not have happened, because the only other approach would have been to, well, the one that I know of would be to fly this over from the parts of the Mississippi onto the lab. You would have to get the rights to fly over people's property, and it would become just this legal nightmare. Like it just would not have happened. You'd have to get permission, right, to fly this like 8-ton thing over your property. Yeah, this probably the risks associated with this, like you have to get the right in case it has to be jettisoned. So there's yeah.
That's a legal requirement.
Yeah.
Do you know how much did it cost?
It was about $3 million, I think. Something like that. Yeah, we saved a lot of money. Yeah. So in celebration, the local brewery, Two Brothers, they created a special magnetic moment beer for the occasion on its arrival. And then 2014, we had the hall ready. This was much better than the Brookhaven hall, where the floor had been built in segments, not anticipating it'd be used for this experiment. And so the segments would move separately from each other and cause the magnet to bend and change its shape and things. This one has an almost 3 foot thick monolithic concrete floor. So the whole thing was extremely stable. One thing that did happen, though, was that up over here, people are building the mu-to-E experiment. And at some point, they were excavating this, and it caused just this minute change in the level. And we had to go and change the angle of the magnet again, because just the tiny shifts in the landscape. Okay, I'll skip the reconstruction because I'm way behind. But finally, it's amazing, right? We rebuilt this thing in all of its complexity and turned it on, and it worked just fine. It was amazing after 14 years. Okay, so now what are we going to do? How do we make this experiment work? So the idea is we take polarized muons and we inject them into this magnetic storage ring. It's just like the electron experiment. We have a strong magnetic field, and then we have some electrodes to confine the muons vertically. So what would happen with relativistic particles is that, let's say we injected a muon at this point in the ring. Here's the momentum vector, here's the spin vector. If the g factor were identically equal to 2, these two would precess at the identical rate. So just in lockstep together. Okay. However, because the G factor is slightly greater than 2, the spin vector is going to precess a little bit faster. Okay. So we're going to look at, that's going to be our signature, the thing we're interested in here. So in more detail, and you can just pull these equations out of Jackson. What we look for is, okay, so here's the muon spin precession. Here's how fast a muon would precess in a magnetic field if it were at rest. So this would just be the regular Larmor precession. But the fact that it's moving, you get the Thomas precession, which is this additional term here. Here's the cyclotron frequency. And if you subtract these two together, you'll see that it's directly sensitive to G-2. So the difference between the spin precession frequency and the cyclotron frequency is E times A mu B over MC. There are some other terms that go in here due to the fact that we don't have a purely magnetic field, we have an electric field as well. But you can make this term here. So the problem with this is that, okay, if you want to do a precision measurement, it's extremely hard to measure, say, an electric field to sub-part per million precision. So we wanted to get rid of this term. The way you can do that is you can pick your momentum such that this term in brackets disappears. We call that the magic momentum. It's 3.1 GeV. So that makes this term go away. The other thing is there's a small term from the pitching motion of the muon as it goes around the ring. It'll undergo simple harmonic motion because we have to focus the beam, and that we will have to correct for. But basically, what we do is we take the difference between spin and cyclotron frequency. We call this the anomalous precession frequency, and that's proportional to the thing we want. Okay, so we do two things. We measure the muon anomalous precession frequency, omega A, and then we measure the magnetic field. So if we measure this and we measure this, we know the charge to the mass, we can get A mu. That's the job. Yeah.
When this discussion, you put the momentum, but the principle as
it's taken into account. We have very detailed, yeah. But yeah. So these correction terms account for some of that. They're detailed, heavily detailed spin tracking codes that account for this. But basically, these are the forms of the corrections. Yeah. Okay. So not all of our muons are identically at this momentum. So we will in the end have to make a correction for those that are off the magic momentum, and we will have to make a correction for the so-called pitch correction. But these are under control. But these are pretty much two of the only major corrections we make to what we measure. Okay, why did we go to Fermilab? We went to Fermilab because we couldn't get at Brookhaven. We were statistics limited, and the advantage at Fermilab was that we could just do the experiment, but more frequently. Okay, we didn't want to put in more muons at a time. I should tell you more about how this works. What you would do is you would take protons from the booster, send it around this recycler ring. They would hit a target, and from the target, you make a bunch of pions. So here's the target, sorry. The pions, we capture them and they decay into muons, and we capture the muons. They make a few turns around this delivery ring. And basically, all of the pions decay into muons. So we almost have a pure beam of muons, which we then inject into our experiment. And we would do that. We'd inject 8 pulses of muons. There'd be a 200 millisecond delay, and then we'd inject another 8 muons. And the advantage of Fermilab is that we had this duty cycle here where we were running the experiment about 4 times frequently than we did at Brookhaven. That was the big advantage. But the number of muons we would put in the ring at a time was about the same. Okay, I'm going to have to go very quickly on how the experiment works. So, there are tons of challenges, right? Like, how do you get the muons from here into here? So one of the main problems is that inside the storage ring, it's a 1.45 Tesla field, and you can't just take muons from basically 0 field into 1.45 Tesla because you'd have to necessarily have magnetic field gradients, and the beam will just disperse. Every muon would see a slightly different field. The whole thing would be dispersed. So there's a very clever idea to make a so-called superconducting inflector. You basically cancel the magnetic field. So the muons don't see any magnetic field. They come in straight. And then there's a very short transition of the order of a couple of centimeters or so, where the muons go from 0 field to 1.45 Tesla. using superconducting technology, conducting shields. It was a very, very clever idea. So it lets the muons get in the ring, and there's essentially no perturbation from, even though you have like 3 Tesla fields just a few centimeters away. These superconducting shields are absolutely amazing. The next thing we have to do is, if we didn't do anything, the muons would make their way through this inflector, come around and hit the back of the inflector. So to put them on a stored orbit about 90 degrees away, we have to change the direction of the muons, the muon momentum vector, just perturb it slightly so it will go on to this blue stored orbit. Okay, so we momentarily reduce the magnetic field by about 200 Gauss. But this is incredibly challenging, because what you have to do is you have to make this 220 Gauss field turn on and off before the muons make their way around again. That's 150 nanoseconds. So your job is to make a 220 Gauss field that turns on and off in 150 nanoseconds. That's an incredibly challenging job. It involves thousands of amps of current going through these things. It's really, the hardware for this system occupies basically this entire wall over here. The final thing is we store the beam. To keep them confined vertically, we have electrodes. They cover about 43% of them, and they keep the muons stored. And what that results in is that the muons are going to undergo simple harmonic motion as they go around the ring. Okay, so we need the muon spin direction, right? That's the thing we want to measure. So what happens is our muons, they get stored in the ring. Eventually, they'll decay to electrons and positrons and neutrinos. The decayed positrons are going to spiral in and hit a calorimeter. And this is one area where nature is being very kind to us. Like normally you ask someone, okay, tell me what direction the spin of that particle is pointing. You have to do a lot of work to figure that out. But here nature is very kind, because there's parity violation in muon decay, where if you go into the rest frame of the muon when it decays, the highest energy positrons are preferentially emitted in the same direction as the muon spin. So it becomes like a searchlight or something for us. So here in the lab frame, if you look, here's the momentum vector of the muon. When the spin vector is pointing in the same direction, in the lab frame, the decayed positrons have the most energy. When the spin vector is in the opposite direction, they have the least energy. So we have the signature telling us in which direction the muon spin is pointing. So we just basically put a threshold here, and the number of muons, decayed positrons in this area here varies like cosine omega 18. So we just have to get this frequency, basically. Okay, so what should our signal look like? Well, we expect our muons to decay, and we have this spin precession. So the thing we get is, we call it the wiggle plot. So you have this exponential decay, and superimposed on top is this wiggle from this precession. And so normally, you would try to fit this with a 5-parameter fit. Depends on the number of muons you had, the relativistic lifetime, the amplitude for the oscillation, its frequency, and some starting phase. If you do that, it works pretty well, but there are these enormous residuals, and those are due primarily to beam dynamics effects. So the 5-parameter fit is entirely inadequate, and this was discovered at Brookhaven. And just as an example of one of the beam dynamics effects, we talk about one of them, which is the coherent beam motion. Okay, so here's, let's follow a muon as it makes its way around the ring. Okay, so going from here to here, this is one pass through the ring. So the muon will execute simple harmonic motion. So in the radial direction, it moves out to outer radius, back into the inner radius, and then back again, and so on. So let's say you're a detector here. The first time the muon comes around, you might be close to the outer radius. The next time around the ring, you're slightly closer. The third time around, you go around the ring, you're even closer. So the muon, every time it goes around, it's getting closer and farther away from each detector. The problem this causes is that you're effectively, the acceptance of this calorimeter for when this muon decays is changing as a function of time. Okay, and so this causes, so you will see these frequencies superimposed on top of your measurement because your acceptance is changing. So there's this apparent breathing in and out of the beam at this alias frequency, the difference between the cyclotron frequency and the betatron frequency. This effect it dephases over time, and it washes out when all the detectors are averaged together, but it's in there, it has to be accounted for. And there are many, many other beam dynamics effects like that affect, the width of the beam, the so-called vertical weight, all sorts of parameters. So we did need instrumentation to tell us what the muons were doing. So we had this 2 sets of straw tracker stations that would tell us what the muons are doing, the stored muon distribution. So we had a good handle on all of these things. Okay, let me tell you about the magnetic field. So I told you how we measure omega A. We have to measure B, and then we can get A mu. Okay, so we have to measure the B field. So the muons, they execute simple harmonic motion in the field. So in fact, they never see like one magnetic field, right? The storage ring magnetic field will vary around the ring. It'll vary vertically, it'll vary horizontally, and we have to know this. So one thing we have to do to make our job easier is just to make this field as uniform as possible. If it were perfectly uniform, we wouldn't even care about this motion. Like everyone would see the same field. So we spent a lot of time making the field very homogeneous. That also is helpful for beam dynamics as well. But making the field homogeneous makes the whole experiment much easier. So here's a cross-section of the magnet. It's a so-called C magnet. So there are 4 sets of coils. Here's a coil here. It has 24 individual coils, each one with 5,200 amps. And so they make a vertical magnetic field. And then the muons are in this region here. So in the little, this is it's about 9 centimeters in diameter. So if you were to measure the field and take a cross section, we would measure the field using NMR probes, get a very detailed map of the magnetic field at this particular location, using this thing called the trolley, and then we march the trolley all the way around the ring and make get these slices of the magnetic field. So there's like 9,000 slices. The whole field map is something like 160,000 points, and takes a few hours. So you think, okay, great, we have B, but in fact we don't have B, because when you put this in the storage ring, that of course has a huge perturbation on the magnetic field. Right. The muons don't see that field. They're in vacuum. So we have to correct for that. There's another issue that we have to take this guy out and put the muons in. So the way we track the field when the trolley is removed is we have fixed probes, 378 fixed probes, NMR probes on the top and bottom. And so when the trolley goes by, we get the relationship between the fixed probes and the trolley readings. And then when we take the trolley out, we just track what happens to these. And from that, we can infer what was going on in the muon region here. Okay.
You have to break the vacuum every time?
No, we have something called the garage. So we bring this to a particular region, part of the ring, and then we retract it. Yep. So the final part, okay, the trolley, of course, perturbs the field terribly. How do we get to something fundamental? So if you go back to what I was telling you about before, the precession frequency of, say, so here's the muon, right? It's precessing in the magnetic field. We need to know the magnetic field. Well, suppose we put a bare proton in there. The gyromagnetic ratio of the proton is known to better than a part per billion, 0.3 parts per billion, I think. So if you were to measure the precession frequency of a bare proton, we know the gyromagnetic ratio, you could get B to a part per billion. That's about the limit of precision you can get in an absolute sense on a magnetic field. But bare protons are too hard to work with. So instead we use water molecules that have protons in them. There, the gyromagnetic ratio is known, it's to about 11 parts per billion. So what we do is we make a probe that has water molecules in it, and we measure the precession frequency of the protons in the water molecule. And from that, in principle, we could get the precession frequency of protons in water. And then from that, since we know this guy, so we measure this, we know this, we get B. One problem is that, in going from bare protons to protons in water, the diamagnetic shielding is temperature dependent. So the gyromagnetic ratio is actually temperature dependent. So we have to take account for this. It's about a 10 ppb per degree C effect. And of course, it's hard. It's the relationship I showed you is for a spherical sample of water. It's very hard to make a perfectly spherical sample of water. So instead, we've used cylindrical samples. And then what happens is that we measure the precession signal of protons, say from over here, But the other water molecules off on the sides, they're magnetized, they make magnetic fields, they perturb the field locally. Okay, so there's a shape-dependent effect that we have to take into consideration. If it were a spherical sample, the shape factor here is 4 pi over 3, this term cancels. But for a cylindrical sample, this is 2 pi. And so there's a dependence on the magnetic susceptibility of water, which is kind of interesting because the best measurement of the magnetic susceptibility of water comes from 1933. We actually are working on an update of this, and I can tell you that it's actually fine. There's no big problem with that, but it's amazing. No one has been able to do better. The final complication is what I mentioned before, is that we don't just have pure water. We have to make an NMR probe. It has to have aluminum and coils and all this other stuff. And so we have to be able to measure the perturbation of these materials on the local field. So we spent years working on this stuff, and we have magnetic field probes that we have characterized so that we know the relationship between what the probe measures and the equivalent precession frequency of a proton in water to 15 parts per billion. So we can measure absolute fields to 15 parts per billion accuracy. And what we do is we take this probe, which is very well calibrated, and we use that to transfer the calibration to the trolley probes. So there's this chain of calibration. And ultimately, we can know the field, what the muons see to 20 to 30 parts per billion. Yeah. Right. We don't do that. Yeah. So we take, we pulse every 5 seconds or something for water, and we just take the hit for that. Yeah. So that's part of, yeah. We take 4 to 8 hours to calibrate a single one of these probes. So we just spend forever repeating the measurement, shimming out the field locally. We spend a lot of time in it. Yeah. So we take the hit. Yeah. So we just sacrifice the time. Okay, I'm going to skip over these complications. Yeah. Yeah.
So I'm a bit confused. What is PR?
Oh, this is the reference temperature at which the gyromagnetic ratio, basically the diamagnetic shielding of protons, was measured. So it was,
Okay, this is different from the PR that next time. So there you had a working point.
no, it's the same one. Yeah, sorry. Yeah, a change in terminology. Yeah. Yeah, so it was measured at 34.7 degrees C. So we reference our measurement to that, and someone else measured the temperature dependence for flowers and peddling. Okay. Okay, so we put, okay, I'm over. I'm sorry. Let me quickly go. We put all of these parts together. The anomalous precession frequency, we take the magnetic field we measure around the ring, we convolute it with the muon distribution. We make some corrections for some magnetic field transients that I didn't talk about. We make the corrections for the electric field and the pitch correction and some other minor terms. When we express the B field in terms of the magnetic moment, we put it in terms of some more fundamental parameters that actually reflect how those original measurements were made. And so these fundamental constants out here, this combination is known to about 25 parts per billion. So we put all of this together and we get our value for A. So in 2021, we released the results from run 1. This is this fraction of the entire data set. And what I'm going to show you now is the result from runs 2 and run 3. So about 4 times the data. We have about twice the precision. And this stuff is in the can. We're analyzing this now, and we should have this out maybe 2025. So we do a blind analysis. We don't know what the answer is. What we do, that wiggle plot, we don't know the time base of that plot. So we don't know that oscillation frequency. And on the very last day, we have external collaborators who check a clock whose frequency is hidden to us. It's in a locked cabinet, and they go and check it. Of course, it's monitored more frequently in that, but they go and check it physically. And so finally, in July, at a collaboration meeting in Liverpool, we unblinded the clock. So we finally figured out what the time base was. And so, of course, it's those of you who work on blind analyses, they're just incredibly stressful. Like, you don't know if you've made a gigantic mistake. The most stressful one, of course, was our first result, where we really didn't know. It's new collaboration. We moved the whole thing. We had no idea where the first answer was going to come, but it was consistent with the Brookhaven result. But you still have the same trepidation when you do it again, and now we're more sensitive. We have more statistics. So this is what we got in run 2-3 in August. So now we've combined all of our answers. So here's the Fermilab average, and then here's the world average here. Okay, so we've reduced the uncertainties by about a factor of 2, more than a factor of 2 overall. So we're now down at 190 parts per billion. Okay, how does this compare with the theory? Oh yeah, first, of course, okay, made the news again. Some crazy BBC. Normally I think of that as a very kind of serious, low, understated kind of thing, but no, scientists at Fermilab close in on 5th force of nature. Like, that's pretty extravagant for BBC, and of course totally misleading. And then other things were a little more sedate, I guess, or sober. But here's the theory situation, which unfortunately has become it's interesting, but also kind of a giant mess. So here's the world average, okay? And this is the result from that white paper I showed you. If we were just to compare these, there's a 5.1 sigma standard deviation difference between these. Okay, so that's a serious discrepancy. But since this result came out, there have been a couple of developments. The biggest one is that this hadronic vacuum polarization term I told you about, people have figured out how to do that on the lattice. Okay, so a completely independent method. And this is a real tour de force. This is a sub% level calculation of something which is horrendously complicated. And it's just that hadronic vacuum polarization term differs from that which is based on the data. Okay. The other thing which happened recently too was that a collaboration, the CMD3 collaboration, released new data on E plus E minus going to pi plus pi minus. So this low energy region I talked about, which is most important, and their measurement of that the R ratio down there differs from basically all the other experimental measurements, but it would be kind of in agreement with the standard model. So all of these things can't be true at the same time. Okay, something has to be, there's a problem here that will have to be resolved. There's a lot more data. This E plus E minus scattering data is going to BABAR, BEL3. There's going to be a lot more BEL2, BES3 are all going to have updates, which will be very high precision. They will make an important contribution to the hadronic vacuum polarization. There are other lattice groups. I can show you a plot of what they're finding, but basically other lattice groups are agreeing with this measurement. It's not some mistake made by the lattice group as far as we can tell. It's a good question. That's a very good question. Let me get back to that. Okay, we're going to get a new result maybe in a year and a half, 2 years, where we will reduce this another, say, 50% or so. The JPark experiment at JPark is going to they'll probably have a first result in 2030 with probably the Brookhaven level statistics, and then over the course of the years, they'll get down to the Fermilab. Yeah.
This green thing we use experimentally.
Yes. Yeah. This is lattice. Yes, exactly. Yeah. So here's the problem. So that the lattice result came from this BMW collaboration. So here's, if you look at the hadronic vacuum polarization term from them, here's their result. This is what the E plus E minus data show. So they're different by a couple of standard deviations. Well, yeah, it's hard, right? Like, let me show you. Here are results for E plus E minus pi plus pi minus from a whole bunch of experiments. Okay, so this is the latest one from CMD3. Here's BABAR and Chloe. Like, Chloe and BABAR disagree at 2 or 3 standard deviations. So there's not okay. It's not these are basically consistent with each other. Like, the experiments are basically consistent. But the point that was raised about, okay, this comes over decades of work. Not all of it was blind, and because people it's much newer in physics now to do a blind analysis. This was a blind analysis. And so, people may, you look at measurements of the gravitational constant, or the neutron lifetime, or think, they track each other to some extent. So there's something going wrong here. If you compare this result with this result, so you put the absolute cross-section measurements on top of each other, these are clearly different from each other, right? They cannot both be true. So the question about the lattice, I was at this Bern workshop, and it was raised explicitly that the lattice groups have to try to do a kind of blind analysis, and they're trying to figure out how to do this because it's hard for them. Yeah. Yeah. So here was the BMW result, and then other groups. There's this so-called window technique, a very clever idea, where the lattice, of course, is difficult because ideally you'd have infinitely small lattice spacings and infinitely large lattice volumes, but you can't do that. But there are these regions where you can take the so-called window region where the systematic effects with finite lattice size, finite volume are under control. And so many groups have done calculations in that region. And it turns out you can map that onto the experimental data. It corresponds to particular values, particular range of square root S. And so the lattice groups are kind of in agreement with each other and differ with the E plus E minus data. So it's really interesting. It's just, I wish it had, everybody had agreed with each other. We had something to compare with, but it's interesting. So, who knows what's going to happen. One thing I will say, there's a whole new approach to measuring this hadronic contribution by doing elastic electron muon scattering, where the running of basically the running of alpha depends on the hadronic vacuum polarization in some sense. You can relate the two, where basically the running of alpha has a hadronic contribution to it, and if you separate the QED part from the total, you can isolate the hadronic part and put it in here. It's incredibly challenging, but it's an entirely independent approach. Okay, I've gone over. Yeah. The mass of the muon. In which one? The So yeah, the mass of the muon is known to 22 parts per billion. It does not affect the precision of any of these results. Yeah. Okay, I need to stop. I could talk about this forever. Okay, yeah. So thank you. Yeah.
Thank you for that. We have started the question. The phone has a question.
Yeah.
If you just solve for that error and you get like that, like total part,
right? That is a good point. So that's the part that's scary about this, is that if you look at the discrepancy, let me go back here. Well, I'll show you for the Brookhaven result. All right. Okay. Here's the weak term, 153 times 10 to the minus 11. Then we go to the discrepancy. $268. It's bigger than the entire electroweak sector contribution. So it's a huge amount. It's stunning, right? It's as though we missed an entire sector of particles. Yeah. Yeah. So that it makes it challenging to explain. Okay. So, the fact that LHC has not seen anything with, these, there of course are theories the theorists are incredibly creative people, so they find places where both, all these things could be true at once, where you could have an entire, large contributions and yet have not seen anything else elsewhere.
Symmetry.
Yeah. But there are these corners in parameter space where this is possible. Yeah. But it's good. Yeah, I should have pointed it out that this is larger than the whole contribution of the W and Z bosons. So it becomes very hard to explain. And now the other side of this is that the hadronic vacuum polarization. So we'd say, well, all those E plus E minus measurements are wrong. Then maybe that was wrong, and so the prediction is wrong. But then if you perturb those too much, you perturb other parameters in electroweak fits for the WMass. The way all of those parameters hold together is also highly interdependent. So the running of the couplings, they're all they all are sensitive to that same E plus E minus, like the underlying physics there. So you shift the tensions elsewhere. Yeah.
The CMP3 is saying that there is no problem.
Right. But the thing is that if you take that, that gives you different values for the running of the coupling, which then changes for, what you would expect for the value of the coupling at the Z mass and stuff like this. So it becomes, right. You can't. So people, this window stuff I showed you, people are now exploiting this to try to figure out exactly where these anomalies could be hiding. And, you don't have to affect the electroweak fits if all of the anomalies are at very, very low energies. But then that's where you have these tons of experiments, which are kind of in agreement for the most part. So it's really.
You're saying even if there is somehow you manage to agree, it's going to break.
It'll break something else. Yeah. So it's like a bubble or a balloon, right? And you're squeezing here, but it's getting worse over there. Or it gets better here, or it gets worse there. Maybe those are lesser discrepant, like less important in some sense. Yeah. But
Invalid question.
Yeah.
What is your result?
Yeah. Okay. So that's
You're using the same range.
We get. Yeah.
I'm sure you get that.
I get that question, and I said that crazy. The last time I got that question, I just kind of said, well, the muons are in vacuum, and what I meant by that was that if we go, I hit that slide. If you look at what the muon sees, it just sees a vacuum tube, right? It doesn't know that it's the same experiment as before. It would have to be something like, right? It doesn't know that. Yeah.
You're using the same technique.
Yeah, but it's
You're
much,
measuring things in the same way.
yeah. So we so there would have to be something wrong in it, but everything kind of hangs together, right? The
You're saying something is not hanging together.
well, the experimental results are consistent. We would need something wrong in the method, right? But everything we try. So I didn't show all of the every single systematic quantity is done by two independent groups. But we're talking about something that has to be wrong in the method, right? Yeah, and we just haven't come up with anything. It would have to depend on some parameter, right? That I think is, where the dependence of the anomaly on that parameter is different than what we expect. So we've varied the parameters, right? We have varied the magnetic field strength, we've varied the quadrupole strength, we've varied these things and seen how they track. Not over a very sensitive range. Like ideally, we do, we change the magnetic field and do it at a different magnetic field or something, but over the extent to which we can see things, they track the way we expect them to. So it would have to, it would have to be something fundamental in the method that we're overlooking, and we can't think of it. Yeah. Like we haven't found anything but a few years ago, 5 years ago, maybe there was something about relativistic effects. I don't know if anyone saw those papers on the archive, but it was like an SI versus CGS problem. And they were off by like factors of 10 to the 7. But like it was just, yeah, no, it was too bad. Otherwise, it would have been an interesting kind of discovery, but like a GR style effect, it's just impossible. Yeah.